In this video, we're going to look at the output resistance for our series shunt or our voltage amplifier, and then we're going to bring all of these concepts together to make an equivalent circuit for our series shunt amplifier. So what we're talking about when I say we want to know our output resistance, I can define my output resistance as looking into the circuit here. And so notice in the previous two videos, in some cases I said that we had a R0 value of 0. That wasn't necessarily needed, but in this case it's definitely a non-zero value. So a good way to find our output resistance looking into the output is to do something called our test source method. So we're going to use a test source. And so when you're doing this method, what you want to do is you apply some test voltage or test current to our output terminals. So let's go ahead and do that. It doesn't really matter which one in terms of the hand analysis. Of course, if you're actually doing this in the lab, typically a voltage source is going to be easier. It's going to have some value of Vx, and it's going to be providing some current you can measure, Ix. And so this output resistance then is of course going to be equal to Vx divided by Ix. So if we think about doing this in the lab, that's relatively simple. We just apply some voltage and measure a current. Not quite so simple with our hand analysis. One important thing I forgot to mention up until this point, when we're using our test source method, what we want to do, or what we need to do, is we need to deactivate independent sources. So deactivate independent sources. So these diamond voltage sources are dependent, so we don't need to do anything with those, but over here we have this VI source. So in order to deactivate this, we're going to replace all of this with a short circuit. So we're going to get rid of VI entirely, and we're going to replace it with just a short circuit here. And so again, notice we are still assuming that this input resistance Rs is equal to 0, just to simplify things. Okay. So one other thing we can notice as well is that now instead of being Vout, this is Vx, so that this value here becomes beta V times Vx. So now we're ready to do our analysis and figure out the value of our output resistance. So let's start by doing a KVL over here on the left side. So if we do KVL on the left, now we don't have that input voltage, so what we're going to get is we're going to get that our epsilon, V epsilon, is equal to negative of our feedback voltage. And as we just said, our feedback voltage is beta V times Vx. And so that, of course, still has that negative sign out front. Okay, so now let's look at the right side of our circuit. In particular, we want an equation for our Ix current. So we can solve for our Ix because we know the voltage across the resistor R0 is just going to be the voltage difference of the voltage sources on either side. And so of course, if we want to use a positive sign from passive sign convention, we can define our polarity in that manner there, with the positive on the right, such that our current goes through a voltage drop. So our Ix is then going to be equal to, let me scroll up so we can still see the circuit, Vx minus the voltage on that dependent source, which is AV times V epsilon, divided by the resistance R0. So now what we want to do is we want to take this value of V epsilon and we want to substitute it into this equation here. So doing that, we get that our Ix is equal to Vx minus AV times a negative beta V Vx, all of that divided by our R0. And we can, of course, factor out a Vx in the numerator, so Vx times 1 plus beta V AV divided by R0. And from here, we can pretty easily rearrange to solve for our output resistance, which remember previously we had said was Vx divided by Ix. So using the above equation, so using this equation here, we find that to be equal to R0 divided by 1 plus beta V AV. So we see in this case, we have a decreased output resistance. And so I say decreased because we're dividing R0 by this 1 plus beta V AV, which is typically going to be a relatively large value. So decreased output resistance. And just like we saw for the input resistance, this is going to be a desirable trait for voltage amps, for voltage amplifiers. And so just like with our input resistance, we can consider a very simple voltage divider to see why that might be. So if we said here was our V output from our amplifier, and we have some output resistance associated with that and some load resistance. So here's our R0F, and here's some load resistance. Well, of course, we want this V out to be as close to our V out amp as possible. So we know V out in general is V out of our amp times RL divided by our output resistance plus RL. And so if we say that our R0F is much less than our RL, we can make an approximation here and say this is approximately going to be equal to V out amp. Because we have our RL dominates and we have RL over RL is 1. So that is what we want to have happening there. So now we can take this information of our input resistance and our output resistance, and we can draw an equivalent circuit for our series-shunt ideal topology. So an equivalent circuit. And so what that's going to look like is it's going to be a lot more simplified than that big messy drawing that we had a few videos back. So we're going to have our input with some input resistance, the input resistance that we calculated in our previous video, some dependent source, the output resistance that we have just now calculated an equation for, and then connected between our output terminals we'll have some load resistance. Okay, so we have here would be our VI, here is our RS, this would be our R sub IF that we calculated in the previous video, and this is our R sub OF that we just now calculated. This would be our output voltage, this is our load resistance, and so everything inside here is our amplifier with our feedback included. And so we can define a couple things to make this a little easier. So if we want to define a voltage here, we can call this VI prime, so our primed input, in which case this dependent source is going to have a value of AVF. So remember, AVF was our closed loop transfer function that we found a few videos back, times that VI primed, and this is then going to give us our equivalent circuit for our series shunt or our voltage amplifier topology.